concerning the dinner tonight. You'll receive very shortly an email with directions, information, and a Google Map link, okay? I will put a list, we had just redo it, and for financial reasons, I need everybody of you, I put all your names, those who signed up. If anybody hasn't signed up and want to go for the dinner tonight.
Sign up for what?
For the dinner.
Sorry.
For the dinner.
Oh, okay.
Well, you were scared there was something worse, so. And I'll put this list here, and I would like you to, well, you have to sign, okay? That's important.
The people who signed up will have to sign again?
Yeah.
No, just put your signature there that you are really participating.
Yeah.
It's not just a printed list, because we need it for the funding agency that you are there.
All right. And well, the other thing is, everybody has given a talk and has done it on their own computers. Could you please use your USB stick and put it here on this laptop? Sometimes it will break. Or if you wish, you can send it to me per email. Because we want to put all the talks online. So far, we have only a few and most of the videos, but the slides are much more interesting. Okay, thank you.
Okay. Now we'll have Fischer, who is going to tell us about mass generation and the phase diagrams. Please.
Thank you very much. And big thanks to the organizers. It's a great pleasure to be here in Brazil again. Also on request of the organizers, and since I realized that this is a meeting basically focusing on PANDA physics, I enlarged the scope of the talk a little bit. So I will not only talk about the restoration of chiral symmetry at finite temperature or chemical potential, which takes place or is associated with the phase diagram of QCD, but also what happens in the vacuum, namely the mass generation business in hadrons, and I will discuss several effects that are associated with this. So I will briefly introduce in this concept of generating mass from nothing, and the equation that will be in the center of that bit is the Dyson Schwinger equation for the quark. I will then talk about ordinary and exotic hadrons and the effects mass generation has in these. And basically all of the material that I will talk about is covered in this review article, which appeared 2 years ago. And then in the last third of the talk, we will have a look at the phase transitions and the QCD phase diagram. And this material is presented in this review, which appeared on the archive last year and is now in press. Now, what we would like to understand in all detail is how does it come that the mass of the proton is so much larger than the mass of its primary constituents, the up and down quarks, which get masses from the electroweak interaction of the order of 5 MeV. And the question is, how does this make up for the 940 MeV roughly of the proton mass? And of course, we know the answer. Well, it's a strong interaction that generates mass of roughly of the order of 350 MeV. And this mass generation effect is primarily independent of the flavor, and it's the combined effect of these two effects, the dynamical and the explicit symmetry breaking, which generates the infrared quark masses that we see today. And this is a very important issue. It has become a Nobel Prize for Nambu, who investigated this mass generation mechanism in a very simple model. And we will see how this proceeds in the more complicated framework of these Dyson Schwinger equations. We're working with QCD. So we're working with the Lagrangian of QCD. And then the aim and the challenge is to work with this tower of equations that are the Dyson Schwinger equations and make as few or as well-educated approximations as possible to preserve all of QCD's interesting phenomena. And there are several levels where you can work with this truncation. The simplest level is on this level of this equation here. On the left-hand side, there is a quark. This is a propagator which tells you everything you need to know about how a quark propagates in time from A to B. And on the right-hand side of this equation, you have the similar object, but this time the bare one in the absence of any interactions. And then you got a Feynman diagram, which tells you what are the possible ways this quark on its way through time and space can emit a gluon and absorb a gluon again. These diagrams all have a typical structure. There's a bare quark-gluon vertex here, the one that you know from perturbation theory. There's a fully dressed on the other side. There's a fully dressed gluon propagator here, and again, a fully dressed quark. That already tells you that you need to solve this equation self-consistently, because this fully dressed propagator you want to calculate appears on both sides, and you have to do an iteration procedure to solve for that quantity. And of course, the input you need is the gluon and the quark-gluon vertex. So how do you get these? Well, these guys also satisfy their own Dyson Schwinger equations. That's the one for the gluon, and this looks horribly complicated, and it actually is much more complicated than the one for a quark. Don't worry about any of the details. I will also not go into any technical details of how we deal with these equations, because this is not suited for this audience. But the main point to take here is that complicates pile up, complications, right? You have non-trivial 3 gluon vertices in here. There are even ghost gluon vertices and so on. And again, these satisfy Dyson Schwinger equation for the vertices. And in these equations, 4-point function appears, 5-point function appear, and so on. Fortunately, we have managed to devise an approximation scheme for these higher order 3-point functions, which closes the equation. And this is shown here. So we have approximated all the higher Green's functions, again, by propagators and vertices. So this is a closed system of equation. And this is about the most complicated thing that we're able to do today. And I will later on present you results that are really calculated in this scheme. So Richard Williams and Marcus Huber are able to solve this whole thing more or less self-consistently. In many applications of Dyson Schwinger equations, you do not have to go to this complexity. It actually turns out, and we have heard this in talks previously at this meeting, that it is a very good approximation for certain type of physics to work in the so-called rainbow ladder approximation. What you do in rainbow ladder is you take this gluon here and marry the dressing function of that gluon with the one from the quark-gluon vertex in a certain approximation into a model. There is a well-investigated model, the so-called Marx-Tandy model. Again, we heard this in other talks. And you can actually do a lot of very, very interesting physics using this model. And I will start out later, present results first with this simple model, and then at some point come to the more complicated things. Okay? So this is the only technical detail you have to keep in mind. There are several levels of approximation. The simplest, I believe, preserves the important issues of QCD is the rainbow ladder truncation, but there is more, and we can go well beyond this rainbow ladder with sufficient enough effort. No matter what you do, in all of these frameworks, the general picture is like this. Your quark propagator is characterized by 2 functions, a quark mass function, which knows about chiral symmetry breaking and dynamic mass generation, and a wave function, which we call Z. And these 2 functions are shown here as a function of space-like momenta. And clearly what you see is that at large space-like momenta, there's not much happening. You basically see the mass of a current quark. And then when you go to small momenta, the mass generation starts, and you get something like a constituent quark mass at very, very small momenta. So this calculation nicely tells you how these 2 early pictures of QCD, constituent quark masses and current quark masses, are actually just 2 sides of one and the same quantity, namely the quark, which just appears to look different at large momenta or at low momenta, but it's the same object. And you get similar variations for the quark wave function. Actually, you can even say from this value here that this looks like a non-composite object, whereas at small momenta, this deviation from 1 tells you that the quark is a highly composite object there, composed of gluons and current quarks and so on. And we had a nice talk by Fernando Navarra that explains this issue. Also about the flavor effects, right? When you now combine the different masses generated from the electroweak interaction and the strong, you get these different quark mass functions for the different quark flavors. So that was already the introduction. I walk you now through different types of hadrons and try to explain what briefly what we can do in different hadron sectors. I will start out with the baryons, then have a brief detour to ordinary mesons, and then we come to exotic mesons, namely tetraquarks. And I will motivate this by physics. What is shown here is an early version of the baryon spectrum, the ground states and the excited states, as it was known in 2001. Here you see the different quantum numbers. Here we have the positive parity guys. Here we have the negative parity guys. So here this is the nucleon tower, and this is the parity partner. And these things have been calculated with quark models. This is one particular version of the quark model developed in Bonn by Loring, Mage, and Petri. What you see here on the right-hand side is the experimental situation as known in 2001. And on the left, you see the quark model with two different parameter sets. Again, don't worry about the details. The point I want to make is that at that time, in basically every quark model that you got, you obtained a certain level ordering between the first radial excitation in the nucleon channel, the roper, and its parity partner, ground state, which was wrong as compared with experiment. Experiment sees the roper with a lower mass than the corresponding 1/2 minus ground state, whereas all the quark models see it the other way around. And this is really a generic result of the quark model, and you would like to understand why nature is different. And I will offer an explanation. So how do we do this calculation? How do we calculate baryon masses and wave function? Well, we use an equation which is called the Faddeev equation. That's this object here in diagrammatic notation. What you see on the left-hand side is a symbol for the wave function of the baryon. On the right-hand side, you see certain diagrams. Again, the wave function of the baryon appears. These are our friends, the fully dressed quark propagators. And then there are irreducible three-body interactions between the three quarks in the baryon and two-body interactions between each pair of the two quarks. We actually learned over the years that we can neglect these three-body forces simply because they vanish to leading order. And Helios Sanchez-Alepos and Richard Williams actually had a preliminary calculation which shows that also the next to leading order is quite small. So to a very good approximation, the nucleon or the baryon is built from two-body forces inside. That also motivates another approximation, the so-called quark-diquark approximation, where you assume that there are strong correlations between two quarks inside such a baryon, and these are precisely generated by these two-body kernels here. So in this rainbow ladder approximation scheme that I introduced earlier, these two-body kernels are just given by one gluon exchange, dressed with this Maris-Tandy model that I told before. And this is what the results of such a calculation I will present in the next slide. There have been initial calculations beyond this one gluon exchange, but I think it's fair to say that these are still on the exploratory level. Okay, so what do you get? When you take this, you take the Maris-Tandy model, you calculate your quark, you solve this Faddeev equation. This is the spectrum that you see. Here we see again the nucleon type states, the positive parity 1/2 plus, the negative parity 1/2 minus, and we also calculated the 3/2 plus and 3/2 minus states. The color code is the available experimental quality of the corresponding states in the particle data booklet. And the blue states are the ones that have been calculated in this quark-diquark model. And the first thing you see is that there's really a one-to-one correspondence between every state you find in this quark-diquark calculation and every state which is there in experiment. So below 2 GeV, we see no trace of the missing state problem that has been advocated in the early days by quark model people who found lots of states in excess of the ones that have been found experimentally. I think this problem, at least below 2 GeV, is gone. You might wonder, how good is this quark-diquark approximation? Well, we also managed to calculate some of these states in the full three-body framework. And these are these black results here. And where we can do the calculation, the results more or less match the one from the corresponding quark-diquark calculation, with one exception here, which we need to look into more detail. The striking thing is that in both frameworks, in the 3-quark and in the quark-diquark, we obtain the correct level ordering between the Roper, which is lower, and the 1/2 minus ground state, which is higher. And the question is why? Why do we get different results than you obtain in the quark model? And the explanation, and I believe that Chen is going into this also well in a later talk today, the explanation is, well, our wave functions are much more complicated than in a non-relativistic quark model. And because of this, because they are relativistic, they contain more structure. And this more structure is very important. Let me briefly explain this. In a non-relativistic framework, you build up your baryons from 3 quarks, and if you have 1/2 plus, there are 2 possible spin configurations, 1/2 and 3/2, and there are 2 possible configurations of angular momentum to generate the correct parity plus, namely 0 and 2. And the reason is that in a non-relativistic framework, the parity is uniquely given by -1 to the power of the number of angular momentum that you have. And this really is a 1-to-1 relation. In a relativistic framework, this is no longer true. Angular momentum is no longer a conserved quantum number, so this 1-to-1 relation is gone. And that means your wave function can have p-wave components, components with L equal 1, and still have the correct parity for the nucleon and its excitations. And in fact, in this Peter-Sapir framework, the whole baryon is made up of 64 different components in the wave function. And of these 64, there's a sizable number, namely 36, have this p-wave property. 8 are S-wave, and there are even 20 D-wave. And now when you look at the different composition of the nucleon and the first radial excitation, the Roper, you see that the composition is actually very much different. The nucleon mainly consists of S-wave components. There's a third p-wave here, but the S-wave is dominating. The Roper, it's the other way around. For the Roper, the p-wave components are dominating. And these are absent in the quark model. And this, I believe, is the crucial difference between a quark model calculation and a calculation here in this fully relativistic framework. And that explains partly why the level ordering between the Roper and the parity partner is the other way around. Of course, we all know there are corrections to the Roper beyond the simple 3-quark picture. There are a couple channel effects which may bring the Roper down by an additional 100 or 150 MeV. But still, I believe this is the important underlying effect in this picture. And I believe, again, that you will talk about this today as well. Yes. Okay, we can do the nucleon, we can do the delta. We can also do baryons that include strangeness. So this is the spectrum for the lambda-type baryons, again, the same quantum numbers. The sigma-type baryons, same quantum numbers. The double strange ones, the cascades, and the triple strange ones. And again, where we find states, there is nice agreement, more or less, between the states that we calculate and the experimental states. This is not everywhere the case. For example, the lambda 1405 comes out quite different in our framework than the experimental one. But this is actually no surprise because the lambda 1405 is known to be not a 3-quark state. This one receives huge corrections due to coupled channel effect. Another interesting channel is the 1/2 minus in the sigma, where we see 3 states where the PDG only sees 1. But Andres Arantsev gave a talk last year at the Hadron, it's actually already 1.5 years ago at the Hadron conference, saying that in his latest partial wave analysis, they also see 3 states in that channel. So again, I think there is agreement between what we do and what the experimentalists find there. And then all these excited states here are predictions for PANDA. And I think Torot has pointed this out nicely in his talk, that these states will be looked at PANDA, and well, here we are. So this is our prediction for PANDA. Okay, so these were the baryons. Let me now come to the mesons. The baryons we calculate with 3-body equations. Mesons are actually much simpler. Mesons we can do with a simple 2-body equation, which tells you how a meson is built from a quark-antiquark pair. Let me start with the heavy mesons, with the Chamonia. Again, different quantum numbers on this axis, masses on this axis. The PDG values are in blue, and our calculation are the red diamonds. when you go through this diagram, you see that in some channels there's actually quite good agreement. The 1-minus channel is almost perfect. The 0-plus is actually not so bad. But there are other channels like the axial vectors, like the scalars, well actually so these two, where we're just off. I will come back to this in a second and explain why we are off. There are also higher channels where we're spot on, and the 2++ is fine. And actually, since the 1-minus and the 2++ and the 3-minus are on the same redshift trajectory and the same internal forces are dominant there, we believe that the 3-minus calculation should also be good. And it actually matches within 1.5% to a state that has been claimed to be found at LHC yesterday, a couple of days. LHCb 2 days ago. So that looks nice. Now, why does this not work in these channels? And the reason is because we have used a truncation which does not work very well in these channels, namely the rainbow ladder truncation. You can actually frame this in terms of a quark model, potential language. We know what goes wrong. The interaction is simply too simple. If we replace remember we had a fully dressed quark-gluon vertex here and just a bare one here, and when we replace that one with a bare vertex structure, as we do in rainbow ladder, we neglect a lot of spin structure in the vertex, and that damages some of the channels that you see here, and the scalar and the axial vector are two channels which are damaged. The problem becomes even more apparent for the light mesons. Here again, pseudoscalar is fine, vector is fine. You're way off in the scalar and axial vector channels. This just doesn't work at all. Now remember, I introduced in the very beginning all these different diagrams where we calculate these vertices, and I told you we have the possibility to do the calculation in this very elaborate truncation scheme. And actually, once you do that, the situation becomes much, much better. So this is now what we call a full 3PI calculation, including all of these vertex Dyson Schwinger equations. And suddenly, the axial vectors are spot on. There are there's again a one-to-one matching between the states that you find in the calculation and the states that you find in experiment. And the only channel which is still off a little bit is the scalar channel, and we all know that the scalar channel is the most complicated because there may be huge mixing effects between different states there. Glue balls may play a role there. So this really improves the situation dramatically. Now you might ask, why didn't I put the F0500 or some other states here in the scalar channel? Now we'll come back to this in a second, because I don't believe this is a QQ bar state. And this brings me to the third part of the hadron part of this talk, namely the business of tetraquarks. Usually when you think about exotic mesons, tetraquarks, hybrids, glue balls, you start thinking of it in the germanium sector, because many of these states, many potential candidates for tetraquarks or hybrids have been discovered in that sector. But actually also in the light quark sector, we have interesting candidates for tetraquarks, namely the lowest lying scalar meson monet. The mass hierarchy there just doesn't fit a conventional QQ bar explanation. For example, there's no reason why the F0500, the mass ordering of the, well, there's no reason why, for example, the F0980 should have the same mass as the A0980, because the number of strange quarks is completely different there. However, when you think of these states in terms of tetraquarks, everything falls in place. The guys with no strange quark are the lightest. The guys with one strange quark then are the second. And the guys with two strange quarks are the heaviest. So it has been proposed long ago that these states actually could be composed of 4 quarks. And another hint may be the large decay width of the F0500 into 2 pions, which may be related to that quark content here. Let me just flash over this, as this has been dealt with in other talks. These are again the huge excess of exotic states that have been looked at in the germanium sector and needs to be explained. Okay, but let's come back now to the light scalar tetraquarks. How do we deal with these states? Well, since they're tetraquarks, we have to solve a four-body equation. This is the four-body equation in its exact form. This is, again, a symbol for the wave function of the tetraquark. And on the right-hand side, we have, again, the quark propagators and all the possible ways the quarks inside the tetraquark can interact. So there are genuine two-body interactions between pairs. There's a three-body interaction, and there's an irreducible four-body interaction.
You have minus there. You have minus.
Yep.
What's the meaning? What's the meaning?
Of that minus?
Yes.
That comes out automatically. This is when you derive the equation, you get a minus there. It actually corrects for double counting effects here. When you iterate, you get some double counting here, which this term remedies. That's the technical purpose of that term. Now, in order to be able to deal with this equation, similarly to the baryon, we neglect this irreducible 3- and 4-body forces. Also here, we actually have no justification for that. I have no idea at all whether inside a tetraquark 3- and 4-body forces should play a major role or not. This is just technical convenience, okay? But you have to begin somewhere. And again, these two-body kernels are then, what we use is this rainbow ladder framework for these. Now, there's an interesting possibility in these tetraquarks. First of all, that's the wave function of such a tetraquark. This is a highly complicated object, right? It depends on 9 Lorentz scalars, 256 tensor structures, and then there's color and flavor. So this gives you an idea how complicated a complete calculation of that guy would be. But that's not the main point of this transparency. The main point I would like to make is, imagine a quark-antiquark inside this tetraquarks interact with each other. Then what we can have is clusters forming inside this tetraquark. Think about the F0500 that I talked about before. If in the F0500 the quark and the antiquark interact with each other, they could form a pion, and the other one could form a pion as before. So this two-body interaction structure covers the possibility that you can generate, for example, pi-pi clusters inside such a scalar tetraquark. And the interesting bit with being a theoretician is that we can build our equation such that this possibility is there or absent. We can neglect kinematic structure in the equation such that by switching on and off this kinematic structure, we can allow our equation to build these clusters or prevent it from building these clusters and then see how the equation reacts. And this is what we find. If we solve this equation for a scalar tetraquark without allowing for these internal clusters, we find something which you might expect. A bound state with a mass of roughly 1200 MeV. Why is this expected? Well, remember, there are 2 quarks and 2 quantiquarks in there. They all get a mass of 350, 400 MeV in the infrared, dynamic mass generation. You build a bound state with 4 states which have 400, 350 MeV, a little bit of binding energy. Well, yes, you get a bound state with 1200 MeV. That's what you expect. But now we can switch on the possibility of clustering. Dynamic charosymmetry breaking and its breaking pattern tells you we can build pions from that. Pions are very light particles because they are the Goldstone bosons of dynamic charosymmetry breaking. And as a result, we suddenly obtain a bound, well, actually more a resonance mass in the 400 MeV range. This is an effect of dynamical charosymmetry breaking and dynamic mass generation. And this is fine because this is then a 2-pion resonance, and you can easily identify that with the F0500, the sigma meson, which is nothing else than a 2-pion resonance. And this comes out of this calculation. Yes?
Just a short question. What happens if you cluster the quarks, not into pions, but into quarks?
We allow for all possibilities. So they can cluster into pions, in diquarks, and in the other meson combination, which for up and down is, again, a 2-pion cluster. And it's interesting to see which of these clusters is dominant. I have a look at the next transparency. Here it is the pi-pi cluster, which dominates everything. The other components are not so important. We can actually switch them off and verify that the pi-pi cluster is the most important one. But you are right. It's interesting to look at this possibility. By the way, also with strange quarks, you get a kappa and an A0, F0 in the right ballpark. This is not a high precision calculation, right? This is an order of magnitude estimate. Now we're going to the heavy light business, and now we dwell on exactly what you just said. We can have different combinations of quarks inside there. For example, we can have combinations of heavy light diquarks, a charm light quark and an anti-charm anti-light quark that can form a cluster. Or we can have a mesomolecule type cluster, charm anti-light, anti-charm light, or something which looks like people call a hadroproduction, a CC bar cluster and a QQ bar cluster. And this equation allows all of them. And it depends on the kinematics in question, which of these possibilities have the most impact into the equation. That is shown by this graph here. This is actually the integration region, which you test inside the equation in certain variables. And this would be the pole locations of these clusters. And once such a pole location comes inside the integration region, you get not a bound state, but a certain resonance of this type. And we have begun to explore this heavy light framework. Two of my students are actually working on this right at the moment, and the first results are quite encouraging. And that, of course, opens up the interesting possibility of having one framework that can deal with these different possibilities. Mesomolecule type states, diquark, anti-diquark states, hadroproduction states, and dynamically decide which one is realized, instead of making several models for all these different possibilities. So this is very tedious and complicated, but I think there's a lot of interesting possibilities to explore here. Okay, that brings me to the last part of this talk, phase transitions and the early universe. Now we have talked about the effects of dynamical mass generation and the effect this has on the structure, but mainly on the spectrum of hadrons. Now let's see what happens when we switch on temperature and chemical potential. This is my sketch of the QCD phase diagram. Here we have the hadronic phase, here we have temperature, here we have baryon chemical potential. What is known is actually this bit here, the nuclear liquid gas transition. What is also known is this bit here, a crossover between the low temperature hadronic confined to a high temperature deconfined quark-gluon plasma phase with a pseudo-critical temperature of 155 MeV nailed down by our friends from lattice QCD. Yeah, there are two lattice groups, the hot QCD and Wuppertal Budapest, have nailed down this very precisely. And there are question marks all over the place. It's not clear whether a critical endpoint exists at all. It's not so clear what happens here. They're indicating that there's color superconductivity somewhere out there. And this needs to be explored. So how can we determine whether such a critical endpoint exists? What you see here is the so-called Columbia plot. It's a plot which shows you what happens to the QCD phase transition as a function of the quark masses. Here we have the up-down quark mass between 0 and infinity. Here is the strange quark mass between 0 and infinity. Here we have the chemical potential axis, and this is the axis of imaginary chemical potential. Pure gauge theory shows a first-order deconfinement transition. If you lower the masses, this becomes a second-order critical line. Then you get into the crossover region where we find the physical point with physical up, down, and strange quark masses. And in the chiral limit, again, there may be a first-order region here. Actually, the better the lattice calculations are, the smaller this region is. And there's even a possibility that this region goes to 0. And then we have this critical surface, which may bend. And if the second-order critical surface indeed bends, when you start from the physical point and crank on chemical potential, at some point you hit it, and this is your critical endpoint. And the question is this really the case? Now, lattice calculations can be done here at imaginary chemical potential. but not in the real chemical potential region because of the so-called sign problem. I don't go into the details here. So they need to extrapolate in that direction. And this has been done by this group here, the Wuppertal-Budapest collaboration. They calculated the imaginary chemical potential and extrapolated to real chemical potential. And this is the chiral transition, the chiral crossover that they found. And what you see here is the blow up of the error bar of that extrapolation. And at some point, they just stopped the calculation. So this basically excludes a critical endpoint in that region. What is also in this plot is our result from 2014. We find the critical endpoint here. And I will spend the remaining 8 minutes to explain how we find this critical endpoint. Okay, so this is now neither a rainbow ladder type calculation, nor it's this full 3PI framework, but it's something in between. And it's something in between tailored to adjust to the situation at finite temperature and chemical potential. We solve the Dyson Schwinger equations for the up-down and the strange quark, and we back couple the quarks into the equation for the gluon. These are the corresponding quark loops. However, for the pure Young-Mills diagrams in there, we use quenched lattice data, quenched temperature-dependent lattice data as input. The reason is they are corresponding Dyson Schwinger equation calculations, but the error of these calculations is so large that you don't trust them. The lattice input is much better. So we marry the two frameworks. The only unknown function then is the quark-gluon vertex, which you actually model along the same lines as has been shown in 2 days ago. We model this along the Slavnov-Taylor identity for the vertex, which gives us information on the temperature, chemical potential, and mass dependence of the vertex, and the known ultraviolet and infrared behavior. So the remaining uncertainty in this calculation basically comes from the model for the vertex. But I would like to stress that the most important bit, I will argue this again in a minute, is the inclusion of the back reaction effects onto the gluon. Because after all, this is what generates the physics of the Columbia plot. And you would like to include that physics to be able to see whether you pierce this critical surface or not. Okay, the first thing we need to do is a quality check. Does it make sense what we're doing? And we do the quality check where we can compare one-to-one with lattice calculations. What you see here is a quantity which is proportional to the chiral condensate as a function of temperature. And here we have temperature. These are the lattice calculations from the Wuppertal-Budapest collaboration. And this is the first result that we obtained. And when I saw this, I thought, oh, well, this works on a 10% level. That's nice. And then we published this, and 4 weeks later, my student, Jan Lücker, came to me, and he was very turned down. He told me, look, I'm very sorry. I forgot a factor of 2 in the determination of my quark masses. And I said, okay, well, put the factor of 2 in, and we'll see what happens. And this is what happened. So sometimes it helps to correct the little errors, and now we're right on top of the lattice data. Which means we get the same transition temperature. This is actually not a quality assessment. This is because of the tuning of one parameter, but that the slope matches the lattice data. This is non-trivial, and this is really a non-trivial result in quality check. Second quality check, the gluon. Remember, we have input from quenched lattice QCD. This is the longitudinal part of the gluon propagator. This is the input at 3 different temperatures. So this is the quenched gluon, and this is the unquenched gluon, once calculated in our framework. These are the solid lines, compared with the lattice calculation. And let me stress that we had our results before the lattice. So this was a prediction of the approach, which was verified half a year later, thanks by our lattice friends from the Berlin lattice group. And even the temperature inversion. So here, the largest temperature is largest, and then it goes down. Here, it's the other way around. Even the temperature inversion is nicely reproduced by the Dyson Schwinger result. This is the longitudinal part of the gluon. So at finite temperature, the gluon splits into a longitudinal and transverse part, and that's the longitudinal one. This is where you see the most dramatic changes with temperature, actually. If I do what? Yeah. We know, yes. I don't show it, but it's in the review that I mentioned at the beginning. Yes, we determined this. Okay, so having done these two quality checks, we cranked on chemical potential and saw what happens, and this is what happens. So this is, again, temperature chemical potential. This is the lattice exclusion region. So here we have a crossover. This was the analytical continuation of the lattice results I talked before. And this is what we find, a critical endpoint at 117,488 MeV. This green line here is what you obtain when you measure the curvature of the transition line at small chemical potential. You can do that on the lattice and then extrapolate that. So we're actually not very far away from this. This can be compared with the results from heavy ion collision, the freeze-out points. And those are nicely cover the region that we see. And on a different scale, we can also, again, compare this with the possibilities from different experiments. And when you look here and you see where our critical point at the moment lies, this is exactly the range which will be explored at a CBM experiment at FAIR. So this is, if you want, our prediction for the CBM experiment now and the critical endpoint there. Let me stress that in this calculation, let me stress this again, the inclusion of the Young-Mills sector, the back coupling of the gluon, of the quark onto the gluon was absolutely crucial to obtain this result. If you don't do this back coupling, and there are friends in the Dyson Schwinger community, basically Yushin Liu and collaborators, Bengao, so, who employed Maris-Tandy type models for the gluon, and then did a lot of calculation with different quark-gluon vertices to assess the effect of the quark-gluon vertex onto the critical endpoint. These are very, very interesting and important calculation, and the result is that whatever you do, whatever vertex you put in, if the gluon is only modeled, you obtain a critical endpoint which is in that region. So the results vary by 20 or 30 MeV, but they are all in a region which is excluded by lattice. And only if you do this back reaction onto Young-Mills sector and do the calculation self-consistently, you're able to push your critical endpoint out. And there's not much freedom in moving this point. The reason why I criticized yesterday this plot of Stefanov is that it actually shows a multitude of results which have been obtained in very, very simple models where you tune your parameters. And I'm sure that in 90% of these models, they don't even get the right transition temperature because they have been calculations before the transition temperature was known from the lattice. And this means you get points all over the place in your phase diagram. So what the Stefanov plot tells you is that these simple models are just not predictive. You can get anything you like from these models. And this is different here. So the gluon is fixed by the calculation. And what we've done now, or started to do, is again look at the quark-gluon vertex, because this is the remaining free piece here, and calculated corrections to the quark-gluon vertex from this setup that we have here. And we obtain small corrections, but the corrections are all in that region here. So the state of the art, I think, is that there's not, it is very, very hard to think of corrections that move this critical endpoint to a dramatically different region in the QCD phase diagram. This is why I believe this is a kind of a prediction for CBM. Okay, let me summarize. The main goal of this whole endeavor is to provide a continuum framework that can be applied to physics, well, to QCD physics. It can be applied, and I've showed you applications, to spectra, baryons, tetraquarks, mesons. It can be applied to the physics of the QCD phase diagram. I showed you this as well. It can also be applied, and I didn't have time to discuss this, to glue balls. We have first, again, exploratory results there, which definitely need to be improved. One of my students is currently looking at hybrids, and there's a multitude of results for electromagnetic form factors. We also did calculations in the framework of the anomalous magnetic moment. And all this is summarized in this review here. The main challenge of this framework is to get systematic control over the error budget, because there's no real expansion parameter which you can explore to determine these errors. But I hope to convince you that we have a couple of intrinsic control procedures to make this error as small as possible, for example, by controlled truncations, order by order in propagators, vertices, 4-point functions, and so on. And it is very beneficial to compare wherever you can with lattice QCD to get benchmarks for your calculations that explain you how good these calculations are. And this is the strategy that we followed in this QCD phase diagram business. And there's even the possibility to marry the frameworks, to use lattice input as lattice calculation, lattice results as input for your calculations and build upon that. And we're currently exploring whether we can similarly make intense contact to effective field theories. So this is not really high precision physics, but we're aiming at 10% at physics which is correct on the 10-15% level. And this is definitely competitive contributions in many areas. So with that, thank you very much for your attention.
Questions? Just a second.
Okay, from the first part of your talk, I understood that you are at the level you can do calculations with 5 quarks or pentaquarks, or right? No?
Four at the moment.
Oh.
5 is an entire layer of complexity more than
okay,
4.
so let me do a speculative question. When you get the level of 5 quarks, can you treat like the delta like a combination of 3 quarks and the 5 quarks and see what's the percentage of the pentaquark, pentaquark, yes.
That would be a very, very complicated, in principle, yes. In practice, I would say this is a couple of years away. I know that Gernot, your collaborator, actually thinks very intensely on 5 quark states and the way to do that.
Okay, maybe you can treat as 3 quarks and a meson or something.
I think that's the way to go. Similar to a quark-diquark approximation, you would do a baryon meson coupled channel approach, something like this. This is maybe feasible. We have explored that for the tetraquarks. For example, we can do that in a 2-body framework where we combine quark-antiquark pairs into 2 objects and then do the calculation. And the results are very, very similar to the full-fledged 4-body equation in a similar way as in the baryons. 3-quark or quark-diquark are quite similar. So that may be the road to go, yes.
In baryon sector,
Yeah.
Can you imagine any quantities that possibly in reducible 3-body interactions can reveal effects? And second one is, in your approach, I believe you checked 3-body effect, irreducible 3-body interaction.
Yep.
Small in your approach. How do you?
Yes. So the way we did this is the same idea as we set up this 3PI strategy. You take your higher Green's functions and do a skeleton expansion in terms of lower Green's function. And for the irreducible 3-body force, so this guy here, to lowest order, that would look like something like this. A 3-gluon vertex with 3 fully dressed gluons attached. This is the lowest order skeleton expansion diagram for the 3-body force. And that guy actually is 0 because of the color algebra. Luckily. And then the next term would be something like this, which includes a 4-body function, quark, quark, glue, glue. And this has been calculated by Richard and Helios, and they found that this only makes very small contributions. So I can, of course, not exclude that there's more out there which contributes more, but it looks quite reasonable to neglect these. And this argument is not true in the tetraquark 3-body force. This is why this may be a totally different game at all. Yeah.
We're kind of late. Both people who raised their hand are going to be speaking, and they are going to be speaking. One question at most, if it's brief. Where's a brief question? Okay.
How do you go above the continuum from QQ bar or 3-quark? This is not clear to me, because normally when we put, for example, one boson exchange, always we have the continuum. I mean, your 2-body bound state or your 3-body bound state. You cannot go above the continuum. And, but you are able to get a whole spectrum. And I mean, naively, just what is the key point to allow that?
I'm not sure I understand your question perfectly. I mean, I can translate that. I mean, the only problem that we have in calculating excited states is that at some point the poles of the quark propagator are inside the integration region of the beta-Sapir equation, as you very well know, right? And at that point, the only thing that we can do right now is extrapolate. This is how we got this germanium, this highly excited germanium spectrum. We just extrapolated beyond that threshold.
Even the
that's
nucleon.
Probably a different thing.
The nucleon, you have many, I mean, the resonances well above the sum of the 3 quark masses, no?
This is not a problem. This is not a problem at all.
Okay. I will ask.
Yeah.
Okay, I guess we need to stop Fernando Navarra to ask the question, because it will steal the time from the next speaker, who is also Fernando Navarra. Brief? Yeah. Okay.
From what you said,
Yeah.
from what you said, dyke quarks are not just a mathematical artifact, but they seem to be there. They seem to be real, right?
Yeah. However, one has to be careful with the term diquark. I mean, originally, the idea of introducing diquarks was to reduce this many states that you find in the 3-quark system. And the idea was to freeze degrees of freedom by combining 2 quarks into a point-like diquark. And that, of course, then limits the excitations that you can have. Our diquarks are not at all point-like. They have wave functions. They are extended. So in this sense, they just represent the 2-body correlations inside the nucleon, which are generated by these 2-body forces. So in the end, it is more, I would say it's more a mathematical bookkeeping device than a real statement about tightly bound things, because they are not. They are more loose than you originally thought.
And they work equally well for tetraquarks, right?
That also works for tetraquarks, yes. It just turns out that the diquark, anti-diquark contributions to the tetraquark that we calculated are much smaller than the meson-meson contributions, which is interesting in itself, actually. If this turns out to be the case for all tetraquarks, then the diquark, anti-diquark models, Majani or so, are accidentally right? They have no theoretical foundation then, if this would be true for all tetraquarks. So we need to check that.
So that means they are not really true point-like objects.
Okay, guys. Thank you very much. The next speaker is Fernando, and he's going to tell us about germanium in a hadron gas.
I think it's fine. Thank you. Okay, yeah.
Which is your talk.
All right, thank you.
Okay. Good morning, everybody. Thanks to the organizers for setting up this meeting. I just write in here something that I forgot in my slides. It's a very well-known formula that we all know and like, which is the Cornell formula for the potential between a quark and an anti-quark in the case that they are heavy quarks. So this is a constant minus 1 over r. It's like a Coulomb type interaction plus sigma times r, which is a linear confining part. This comes from the 80s, but it was supported by lattice calculations that came later. And today, if you want to parameterize what is the interaction between a heavy quark and anti-quark coming from the lattice, this looks somewhat like this formula. Now, on the other hand, we all believe today that we are seeing quark-gluon plasma in heavy ion collisions. And in this new medium, there is deconfinement. Deconfinement means that you have a quark-anti-quark pair. In this medium, there will be no linear confinement piece. So the interaction will be just Coulombic. And more than that, also years ago, when this series of calculations and the problem started to be addressed, there was an extra piece. You know that there is only the Coulomb part of the potential, but also because of medium effect, it gets screened in a way that you have this exponential piece, which is minus r over rd. Rd is some number which comes from the calculation and from the lattice, and is a quantity which depends on temperature. So at sufficiently high temperature, this Rd is smaller than the radius of a psi. In my case, a Charmonian state, I representing just by psi, a CC bar state. And then what you see is when this condition is satisfied, there is no bound state. There is no bound state essentially because one quark does not see the other. The interaction is screened by the medium. And this was calculated in '86, and it started a whole program. You can say that much of the heavy iron program was based on the idea that we would produce a new medium, and we would see this medium in laboratory because there would be no formation of the psi particle, J psi, or also the excited states of the psi. Right, so this led to the concept of Charmonian suppression, and it was very important at that time, but later, actually, wow, come on. Later, it was realized that because you have deconfinement, the quarks are allowed to move around, and if you produce a pair, it's not only important what happened to this pair, but this pair leaves together with other pairs. So you have the possibility of combining different charm and anti-charm quarks to form a bound state. So even though the binding is just weak and based on this Coulomb part of the interaction, it's still possible to form bound states inside the medium just because of the combinatorics, because you have many quarks and anti-quarks around it, and they can combine. So for this, you need a numerical estimate. And when this was done, the conclusion was, instead of a suppression, there can be an enhancement of quarkonium production. This is very old. This is old. But actually, these two mechanisms, they seem to be still there. And in numerical calculations today, what we believe is that if you add up both effects, this is the number of J psi's normalized by some quantity, which is the number of CC bar pairs. And this is the collision energy. When here you go from NA50, which is the setup of the old SPS CERN collider, to the Rick-Phoenix collaboration parameters, you see that there is, in fact, a decrease of the originally produced CC bar pairs because of this suppression effect. What I said before, it's still true, but there is the other component, which is the marriage between different couples, so to say, which is the recombination effect, which grows with the energy. When you move from here to here, you reach higher temperatures, and you reach a more intense suppression of the originally formed pairs, and also the number of pairs increases and the recombination probability also increases. So when you add up the two components, the purple line is the net effect. So the net effect is a very little rise when you go from this energy to this energy. So of course, this depends on parameters. I'm not addressing the error in the calculation. But from the experimental point of view, what you see is something similar. This is RAA, for those who are not familiar. This is the total yield produced in AA collisions divided by PP collisions scaled by the number of binary collisions. 1 means nothing special is happening. And so this is the RAA against N part. N part is the number of participants, is a measure of the centrality of the collision. When you move to the right, you see more and more collisions and more plasma production. This is a busy plot, but nevertheless, let's look at the points. So these red points here are the Phoenix collaboration data, which is an energy at 200 GeV per nucleon pair, which is much higher than the crosses. The crosses are the Na50 gold-on-gold collisions, also central collisions. And you see that the curves, they follow one on the top of the other. So you see almost the same behavior, in spite of the fact that the energy was 10 times higher. So this means that there is only a minor variation in the number of states, the produced shape size states, with this change of energy. So you'd say that it's constant. Or you'd say also that from SPS to RIC, there is no extra suppression. However, if you increase the energy, you keep increasing the energy and go to the LHC, this is what you see. The squares, red squares, are the J psi yield in the channel mu plus mu minus. The blue dots, they are J psi into E plus E minus. There are two possible ways to reconstruct the J psi's. And you see that they almost agree with each other. This is again RAA against the N part, which measures the centrality. You see that this is peripheral collisions. It is close to 1, and it goes to 0.6. And the line of the plot before was 0.4. So you see that here there is less suppression than the suppression observed before, and this has been called unsuppression. This means that we are increasing the number of J psi's when you move to higher energies. And it's understood in terms of this regeneration or recombination process. So in other words, if you plot the same quantity again as a function of the number of participants, you see this curve I'm shown before. And now you see a model calculation where you add up the recombination component to the dissociation component, and you see this plateau appearing here. So this these are the shaded areas, which are approximately constant, and they show these two mechanisms combined and acting at the same time. Okay, all this is nice, and I finished my plasma part of the talk. So what we really want to know is what happens in the plasma. This is what is interesting from the QCD point of view. However, now comes the main part of the talk. You have to worry about what happens at the very late stages of the collision. So in heavy ion collisions, there is always a hot hadron gas in the end. So it's a sketch of the collision. You have the initial Lorentz contracted nuclei which collide. They produce some very complicated state composed of partons. This thing goes to an intermediate state, thermalizes, expands as a fluid, freezes, goes through a phase transition, and ends up in a hadron gas. This hadron gas lives still 10 Fermi or so. It's a non-negligible time. So we have to worry about what happens in the hadron gas. And so if you have any number of J-psis produced in the plasma phase which survive the phase transition, they are there, and they will interact with other members of the gas, typically mesons. This is essentially mesons at LHC now, but this will be also mesons and baryons when you move to FAIR. So the hadron gas can be suppressed in the interactions, the J-psi can be suppressed in the interactions with the hadron gas in processes which you can study using meson exchange models. For example, here you have a J-psi, which is an interesting object, interacting with a pion via exchange of a D star and ending up in a DD bar. So this is a dissociation of the originally formed J-psi. These are other processes. These are the diagrams of the first work, which is already 20 years old, about this kind of processes. And you can also have the inverse process. In the same way you can destroy the J-psis, you can reform them because you have plenty of these, and they can interact also through meson exchange and form J-psis in the final state. So you have creation and destruction. You have to worry about the balance. From the theoretical point of view, and if you are just interested in QCD and in the hot phase, you hope for nothing happens here. This is the most desired result, is that the system goes through the hadronic phase unchanged. So you have a direct access to the primordial phase of the collision. But you have to check that. You need these models. You have to make the countability of this number of produced and destroyed particles. So you need a theory for that. So I don't go too much into detail here, but one starting point is to use SU4 effective Lagrangians for mesons. And here are they, some of them. And they are made out of combinations of these vector meson multiplates and pseudoscalar multiplates, where you put everything, all the states. You use the SU4 matrix, you construct the Lagrangians, and there is also these G numbers, which are coupling constants, which in principle you don't know, but they benefit from the fact that using SU4 symmetry, you have connections between them. So they have relations among each other, and you don't have to know all the numbers. This is an advantage of using SU4. More than that, you need interactions which were not in the original Lagrangian. So you have to use these anomalous parity terms, which were proposed in that generation of calculations by Suhong Lee and collaborators. And, well, they are different. You have to put them by hand, and you don't know these couplings. Some of them you may know. So, but the fact is, once you have fixed these parameters, which are the coupling constants, you have a good starting point. So you have a Lagrangian. From the Lagrangian, use everything you know in field theory. You can calculate the amplitudes, the interaction amplitudes. And here, I'm telling about calculation we did, where you can include, we did include pions, rhos, kaons, and k-stars as the mesons in the gas. And with this, you can take the averages and sum over all possibilities, consider spin and isospin combinations, and then you can calculate the cross sections. So you do this, and in the end, when you're almost done, you have to remember that you need form factors. Form factors are usually a shame in effective field theories, not effective of chiral effective theories, but in other effective theories. But you need them first because of a physical reason. You know that these mesons, they're not point-like, they have size, they have structure, and the form factors take into account this fact. By the way, this is why we call them form factors. Also, form factors account for higher order corrections. And finally, they have, if you choose them correctly, they are able to cut divergences when you have to do loop integrals in your calculations when you go to higher orders. For all these reasons, you need these objects. And they contain a part of momenta, which are just kinematical variables. They contain some parameters, which are this lambda. Lambda are the cutoff present in the form factors. And so you have used these two forms, nothing special about them. I will discuss later what happens if you choose a different form, analytical form for the form factors. And the somewhat promising aspect of this is that in principle, form factors can be calculated with QCD sum rules. So you can root them in a fundamental theory. They are for some time arbitrary, but they may not be arbitrary forever. One day you can calculate them from, well, first principles plus approximations, and you know what they are. So it's not so bad to use form factors as long as you can improve their on the calculations of these objects. So you can also use, you don't have to guess everything. You can use the experimental information directly from this decay, for example. D star into d pi is measured, and from the decay, you can extract the coupling constant. You can use sometimes experiment plus VDM, because you can say that D star, D gamma, this you can get also from experiment, but you can also extract from VDM, vector meson dominance. And you can use also heavy quark symmetry, in which D and D star are nearly the same particle. This is a set of approximations you can use. And also you can use SU4 relations, because the number of couplings is large, and you need all the numbers, and you need relations between them. So you can do this. Still, I remember, now, if you want to use QCD sum rules, we did an estimate years ago where you can check the relations and see that they are violated 30% when you treat of heavy particles, and when you involve pions, which naturally should not follow SU4. So you see some deviations from 70%. These are large numbers, but it's not a different order of magnitude. Still, we use what we have at hand now, and with this you can compute the cross sections. You can, for example, coming back to the diagrams I showed before, you can have the dissociation of a pion by a J psi into two mesons, where these two mesons can be D bar, D star bar, and D star bar. And you see the cross section as a function of a square root of energy. The square root of energy is not very high. It's interesting to observe that we are talking all the time about high energy collisions, but there is a part of the collision which is not at all high energy physics. So the energy typical of these collisions is 200, 300 MeVs. The square root of S is only large because of the masses. And also interesting to note is that, as I said, you can destroy the J psis, but you can also form J psis by the inverse reactions, which you can also compute with the same framework. Here, meson 1 plus meson 2 interacts, producing a pion at J psi. So you see the reaction and the reverse reaction, and you see that looking at the scale, this goes up to 10 millibarns and stays there in the high energy piece of the diagram. And this is about the same order of magnitude, almost the same value for the production. So you have destruction and production. It would be nice if using a theorem you could prove that they are exactly equal. This would be best, because then, again, you'd come back to this scenario that in the hadron phase nothing happens. Nothing important happens. But it's not quite the case, as you see. Also, an interesting thing you can do using this kind of theory is to use the effect of the newly discovered resonances. There was a talk yesterday by Marina Nielsen, and this was a review about this new heavy quarkonium having exotic harmonic states. This is one of them, the most famous, the X3872, which is supposed to be a multi-quark state, a CC bar, QQ bar. But also, a couple of years ago, these other particles have been found, and they are charged, some of them, which is very interesting, makes them unique candidates to be tetraquarks. The Z3900 and 4025, they are also combinations of this type, and they can play a role in this game. For example, the J psi against a pion has, once this particle exists, it has a different channel. It can go first in the S channel to a ZC, which then decays into a D and D star bar. And also for the Z prime, the Z prime will affect the interaction of the J psi with the rho, with the production of this resonance, which again decays into D star and D star bar mesons. All this has to be accounted for. It was not previously included in this cross-section. You might say, this is a new ingredient. This might change dramatically the cross-section. But it doesn't. So this is the amplitude you have to include. You just write for if someone is interested. And the result is here. So the black line is without the new resonance, and the dashed lines are with the inclusion of the resonance. So you might have expected they would do a big effect, but they don't. And the effect is only very close to the threshold. Once you are open the threshold, there is a change because of these new resonances, but it's not big, and it is washed away very quickly. Okay, so I have the cross sections, and then I can see what happens with this J psi living in a hadron medium. But for this, you have to move a little and include new ingredients. You need what is called the average thermally cross-section, thermally average cross-section, or average thermal cross-section, which is just the integral of the cross-section weighted with the particle distribution functions, which are essentially Bose-Einstein distributions. This is how the cross-section knows about the temperature. This is the information of the medium. Part of it is contained here. And so you plug the cross-section we have just calculated into this formula, and you get this one. And then you go, well, these are examples of the thermal cross-sections, which are not very important. But with them, we go to this rate equation. So you start to follow the system, and you start with an initial number of J psi's, an initial number of D's and Pi's and so on, and we evolve the system, and they interact and destroy the J psi's and form the J psi's, et cetera, et cetera, et cetera. And you want to see what happens in the end. Oops, let me just... I skip, yeah, sorry. You have gain terms and loss terms, and you see that all these quantities, the cross sections, plus the multiplicities, I just told you, they depend on tau, which is a proper time. And but also with time passing, the temperature changes, and you need to know what happens to the temperature. So you need basically a model of the medium. Ideally, you'd combine this equation with some hydrodynamical code, which makes a realistic evolution of the medium and knows at each instant the position, the momenta, and the number of any particles. But that's too complicated. We have a simplified model for the medium. This was suggested by the ICTP collaboration, which some of you may know, is the exotic particles in heavy ion collisions collaboration. They had the same problem, and the problem to simulate the medium, and they came up with this nice parametrization. So this is the number of particles of a species I as a function of proper time, and you see all these functions, especially the temperature as a function of the proper time. The temperature as a function of the proper time is a falling function, which was parameterized in this way, where Tc is the final, is the critical temperature where you start to have the hadronic phase, and Tf is the freeze-out temperature, which marks the end of the existence of the medium. And also you need a volume, which is function of the proper time. They came up with a parameterization of this medium. I don't go into detail, but these formulas are in the paper. So this represents realistically the evolution of the fireball at TRIC and SPS. At LHC. Some of the parameters are here. So the VC, CRC, etc., etc. You see, they are fitted to reproduce the multiplicities of pions and J size. And then what you get as a final result is this. At the end of the plasma phase, you end up with 0017 J size. And when time goes on, from 8 to 18, which is the lifetime of the fireball, the hadronic fireball, you have a reduction. You could have anything, including no change. But there was, in the end, a reduction, which is the black line if you only consider pions. But if you include rows, it goes down to the dashed line, kaons, the dotted line, and the final line when you include the K stars. But overall, this reduction is not very important. This is a 20% effect. And the same happens at the LHC when you use the parameters of the LHC medium. So it's not very important. It's 25%. You could say that in a first approximation, you might even try to neglect this and see and think that what you see is what happens in the plasma, plus some correction due to the hadronic evolution. And just for curiosity, these to show the role of the anomalous interactions, those which are not in the SU4 scheme. So this is without them, and this is with them. So they produce a reduction of extra 7% in the result, right? Okay, you can do the same thing for the bothonium. It's just change of masses and some details in the theory. And in bothonium is relevant because now we are able to measure bothonium very accurately, including the excited states. This is the upsilon 1s. This is the same RAA versus N-part plot I showed before. You see in peripheral collisions that almost nothing special happens, but when you move to central collisions, the medium starts to make its influence and reduce the number of bottoms. And you see some curves which are theoretical models. All of them, they only discuss the situation in terms of what happens in the plasma. Because the potential changes, because these and other effects, etc., etc. This is a very rich and interesting physics, but everybody jumps from the plasma directly to the data. And what we think is that if one wants to be careful, you should never forget about what happens in the hadronic phase. So you can run this program again and study what happens with the bottom particles in a hadronic medium. You have, for example, interaction of the upsilon, which is the equivalent of the J psi in this case, with a rho or well, it's just rho producing different final states, B star and B, and all the combinations you need. And you do everything, as I said before. You find the cross sections for the absorption of the upsilon and also for the production. Again, you see that they are close to each other. They are almost the same. The thermal cross-sections, this is just to give you an idea of how this cross-section depends on temperature. Yeah? The temperature is running from 0.1, it's 100 MeV, to 180 MeV, which is typically of a hadron gas. It should not be larger than that. And use the rate equation, which I showed before, with the right parameters, and you get the final plot, which is at RIC and LHC, the number of bottoms, the upsilons, as a function of time. Again, running over the time during the life of the fireball, and you see a reduction which is much more pronounced than before. So it's a reduction of about 60 to 65%. This starts to be important. Message is, if you want to study what happens to the plutonium, you should take into account what happens in the hadronic phase. If you don't like SU4 or SU5, go for something else. But the indication so far is that this is really important. This is a comparison between charm and bottom. You see this, the small reduction I mentioned before, and this new reduction, which is of the order of 65%, is important. You should not forget about it. And okay, this is a caveat. If you do not solve the problem of the form factors with QCD sum rules, they introduce a large uncertainty in the calculation. This is what happens. This is the form factor. This is the cross section, one of them, pi epsilon going to BB bar, with everything fixed, but changing the form factor as a function of the energy. So the black line is a Gaussian form factor or a monopole or some other one is a dipole plus something else. From this reference, you see a big difference in the behavior. Also, if you fix one type of form factor and just play with the cutoff, which all of them have as ingredients, so you put this and you see also a big difference. So you have to worry about what happens to the form factors. They need some extra care here. So this is a cautionary remark. And with that, I think I'm done for now. So you have studied the production of and absorption of heavy quarkonium in hadron gas with effective Lagrangian model. We have included pions, rhos, kaons, and k-stars, and also the new resonances, and studied the role of the anomalous coupling terms, and also the form factors. And we have results for the Rick and LHC. And, well, okay, we find some suppressions, weak in one case and strong in the other case. But the most important message for now is that the hadronic phase is important. You cannot just forget it. Thank you very much.
Okay, thank you very much. Thank you very much for being very on time. I didn't even flash the per-minute mark. So we have lots and lots of time for questions. By the way, the sign-up sheet for the restaurant, which everyone going to dinner has to sign, is circulating. Everyone should sign it if it didn't reach you. Where is it now?
It's here, almost here.
Please, yeah.
Okay, I have to sign.
Hello?
I just put it there.
Okay.
Okay, so who is around? Yeah.
Fernando, so I'm wondering, so you said that for the Chermonio it may not be so important, the absorption. But even if you assume that the production and absorption are the same, the kinematics of the final products will be different, right? So this will have an effect on other observables that people look at in heavy ion collisions, such as flow or two-particle correlation, when they use jape size, for example. For the D mesons, it will be, I think, negligible because the production of the D mesons is more than one order of magnitude higher than the
100
C.
times, yeah. For one jape psi, you have 100 Ds.
Yes, so not affect these correlations. But for the jape side, it would be interesting to have a proportion of how much the So I think it's important. Is it possible to have an estimative of how much of the initial production is, let's say you have 100 jape size, in the end, in the final state, you know that roughly 30% is from the hadron gas phase, for example. Because then you can make some estimates on the effect of the D-meson flow, for example. So you have the V2 from the D-mesons, they may be different from the J size. And then in the end, this 30% that is created from the merge of two D-mesons, the flow will resemble much more the D-mesons than the J psi, for example. Yeah. So is there a way to, and also to give kinematic information on the finer state?
Yeah, we can improve on that. From the figure, you see that I started with a number which was something like 0.17 total from the plasma phase. Out of this, in the end, there was 0.014. So you can say in 1,000 events, so you have 17 J psis initially, but then 3 of them were lost during the hadronic phase. So 14 come from the original plasma phase, so they survive. But okay, that's not quite true because it's a game. You know, it's not exactly this same 14 which started that are at the end.
This is my point, yes, yeah. Exactly. So from this 14
yeah.
that goes to the end, how many of them are from the gas phase?
Yeah.
So if there are 7, then okay, so you have 50% that comes from if you look for the V2, for example, then this V2 should be the V2 from the D mesons.
Yeah, the flow would be different for one. Yeah, exactly. So a good point. Yeah.
Here, I have a question. So when you, in your calculations for cross sections, for fractals, you use coupling constants, right? But they are not precisely constant. They are momentum dependent, right? So what's the scale that you need to use? You take the value?
No, I don't take the value. I don't take the value. I just use pure numbers. I agree with you that they should have some momentum dependence, but in this calculation, they were just numbers, right? What you're saying is that I should include some extra dependence in the coupling constants. What I think is that whatever dependence it will be, this will be typically like a log of the momentum, right? Some function involving the log. I expect it to vary slowly with the momentum. So it's a source of uncertainty right now. I could improve this, but in view of the other uncertainties, this is not the first thing to do. This is the first part of the answer. The second is that if you do this exhaustively in QCD some rules, you can then get the momentum dependence from some rules.
Okay. So just have another question. In your bottom-only case, the Lagrangian, is this similar to the SU4 case, right?
Yeah.
It's just
entirely analogous, yes.
I see, okay.
Fernando, it's more a curiosity that I have. When you show the resonance GC, I mean, that you have to introduce and to sum in the cross-section, but you have still an interaction there. I was just curious if that resonance could be generated dynamically by the interaction you have used, because I understand that you compute your cross-section, I mean, perturbatively.
Yeah.
But it is possible to generate the resonances with that interaction, or there is much more to be considered?
No, it is. I mean, people who just think about the resonance and nothing else, some of them, they say, this is a dynamically generated resonance. This is Octet and company, they say that. So you pick a J psi and a pion and let them interact, and they interact, and they re-interact, they will build up a resonance. In their mind, this is what happens, right? So, okay, I have nothing against that. But for me, I'm using the parameters of the resonance. I suppose it exists, like a rho. So you can have a rho in the S channel. You know that rho is a resonance formed by 2 pions. But I'm just using the rho as it is, right, as a S channel line, for example. And I'm using also the resonance in the same way. To account for some non-elementary aspect of the resonance, I'm introducing the width in the propagator. But, okay, that's what I'm doing. I mean, it's not I'm not denying that, but I'm not exploring it fully. I could say just forget about this diagram I have shown to you and consider a different thing. Considering a pi and a j psi re-interacting many times and then producing this dynamically generated state and then decaying. So I don't know. In principle, one thing might be equivalent to the other, but I am not sure. Not sure. This I have to check.
Okay. So when you calculate the cross-sectional amplitude, so you assume the same free space for momentum of particles or very low density and the same amplitude with the elementary cross-section?
Yeah, yeah.
Okay.
Yeah.
But it should be very low density. Hadron gas means.
Yeah.
Otherwise, even kaon production, very low density, but they are influenced already. Momentum are different.
Maybe this is medium effects. We could change the masses, the widths, and everything. But you have to start somewhere, as Christian said.
Okay.
So I
first approximation.
Yeah.
Any further questions? Okay, session closed. We're open at 3, right? Yes. At 3. Anyone forgot to sign this thing Bruno is holding?
Yeah.
Hold it.
I have to.
Yeah.
I have to sign.
And who added the name? Isabella, quem é a Isabela? Não, Gastão não está.
Not São Paulo.
No, it's in the south of Brazil. Well, Marina was here. Well, I take it to her. E depois I'll bring it back to you. Oder du schickst mir per E-Mail bitte, oder ist es zu groß? Ist es zu groß? Ansonsten kannst du mir auch per E-Mail schicken.
Nee, die sind immer zu groß. Das ist heutzutage fürchterlich.
Ja,
es sind 3 Bilder drin und schon ist alles vorbei.
Und einfach hier reinstecken. Ist da noch eins oder ist da nur ein USB?
Gucken wir mal, ob er passt.
Ja, lass es raus.
Genau.
Hier dieses.
Gerade die beiden oben drin.
Die beiden? Ja, stimmt. Für
eine vom ersten und andere vom morgen. Siehst du da, 133 irgendwie. Seit überall Platz ist, fangen diese Programme an, überhaupt nicht mehr darauf zu achten, dass das irgendwie mal transportabel ist.
Ja. Oh ja.
Ja, das ist das Filmchen und so. Ne?
Mhm. Also, wo habe ich die hin? Das sind die 2, glaube ich, ne?
Das waren 2 Stück.